let's look at some key concepts first. Let's define what reaction rate is. Reaction rate is the speed at which the reagents are converted into products in a chemical reaction. And you can define two types of reaction rates with respect to the reagents, the reactants, and with respect to the products. So how fast a reactant is reacting or how fast a product is forming. If we look at first at the reaction rate with respect to the reactant, the rate will be the change in the reactant concentration divided by the change in time. And we have a minus sign here. So if we imagine, for example, that we're studying a reaction which is a compound, reagent A to give you reagent B. If we define the reaction rate of that reaction with respect to A, the reagent will be the concentration of the reagent in the final moment you're looking at. So let's use AF to define it. So minus the concentration of the reagent when you started, or at the time you start measuring that reaction rate, divided by the time that the concentration final is related to, and the time that you started measuring that reaction rate. So initial and final can be either the beginning of the reaction and the end of the reaction, or it could be 2 points in time. So between time 0 and time 50 seconds, even the reaction hasn't finished, or between time 20 seconds and time 60 seconds, whatever. So whatever times you are choosing to measure your reaction rate, you measure the concentration of the reagent in those 2 points. And what the minus sign? Well, because you want the rate to be a positive number, moles per liter, it has to be a concentration units, moles per liter or milligrams per milliliter, whatever, per second or per minute, depending on how you are measuring the time. And it needs to be a positive number, because a speed has to be a positive number. Either it's 0, the reaction is not happening, or it's a positive number, it's happening at a particular speed. It cannot be negative. But when you define the reaction rate with respect to a reactant, because the reactant is being consumed in the reaction, the concentration of the reactant A in the final time will be smaller than the one in the initial time that you have started measuring that rate. So you need that minus sign to make sure that that rate is going to be a positive number. So I'm going to ask you to stop the video and have a go at this exercise. You have this reaction, the composition of hydrogen iodide in gas form to hydrogen and iodide, both in gas form. And the question is telling you, during the first 100 seconds, the molar concentration of hydrogen iodide has decreased from 4 moles per liter to 3.5 moles per liter. So what is the reaction rate? So have a go at try and see solving the exercise. Stop the video now, please. Okay, so how would I go about solving this exercise? Well, I've got the definition of rate. So rate with respect to the reagent is minus a change in the concentration of the reagent, which is hydrogen iodide, divided by the change in the time. So with a minus sign. So I've got the final concentration of hydrogen iodide, 3.5 moles per liter. I've got the initial concentrations, 4.00 moles per liter. And I've got the time that is asking me to calculate this rate, 100 seconds, the first, those 100 seconds. So when I work this out, I end up with a value which is 0.005, and then the units. So what will the units are? Well, they are moles per liter per second, because I'm measuring my time in second. So, and as you can see, it's a positive number. So 5 10 to the minus 3, or 0.005 moles per liter per second is the reaction rate of that reaction in those 100 seconds with respect to hydrogen iodide. In a similar way, we have the reaction rate with respect to the reactant. You can also have reaction rates with respect to the products. And in this case, is a change in the product concentration divided by the change of time. And this time you don't need a minus sign because that value is going to be a positive number. You're going to have more products at the end of the measuring period than at the beginning. So there's no need to add an additional minus sign. And you can define reaction rates with respect to any of the reagents or with respect to any of the products. What is the problem with defining reaction rates in this way? They're very simple to calculate, as you saw in the previous exercise, but the problem is that reactions very rarely stay at the same rate for the whole of the reaction. In general, reactions tend to happen faster at the beginning when there is more reactant and slow down after a while. So that's quite a common behavior. And we can talk a little bit about why that is the case, why they start so enthusiastically and then tend to slow down in a future slide. So the way we have calculated this reaction rate is, it just seems to assume the reaction rate hasn't changed over that period. But that might not be the case. So we need a better way, a more refined way of calculating reaction rates. Have a look at this reaction. It's the reaction of chlorobutane, which is this compound here, with water. And the products are butanol, it's this product here, and hydrochloric acid. So if you look at the table, you will see in the column of the time, it measures between 0, the start of the reaction, and 10,000 seconds. And if you look at the concentration of chlorobutane, which is in the second column, and then you do the rates in between, every 50 seconds, well, more than 50 seconds, every time interval, the rate changes. Molarity per second, that's what the M means. The rate changes. It starts slightly larger, 1.9 10 to the minus 4, and slowly decreases already after the first 50 seconds. So this type of calculating reaction rates, as this is fixed, the reaction goes always at the same speed, and that doesn't matter which interval you pick, is not correct. In most reactions, that's not going to hold. So we talk about the average rate, the average rate over the first 50 seconds, or the average rate between 50 and 100 seconds. And that's a more honest way of describing that rate. It's an average of what's happened during those 50 seconds, during those 100 seconds of reaction. And it's defined, well, in this case, with a minus sign, because it is a reagent, so it's going to be consumed. And as you can see, it's the same formula I mentioned before. But in this case, we don't call it rate, we call it average rate, because we are acknowledging, we are not completely sure that during that time period, those 50 seconds, the reaction rate was always the same. But what we can give is an average rate over those 50 seconds. That was the average speed of the reaction, rather than on each individual second, that was the rate that what happened. On average, that's the rate for those 50 seconds. Another way of looking at reaction rate is not talking about reaction rates or even average reaction rates, but talking about instantaneous reaction rates. And that is saying the reaction rate at that particular point in time of the reaction. In the screen on this slide, you have a typical curve of how penicillin, in the absence of stabilizers, behaves. Penicillin, if it doesn't have stabilizers, is unstable in solution. So when you first prepare it, yes, everything is penicillin, but over the course of several weeks, up to roughly 6 months, it slowly decays and you're losing the amount of penicillin you have in the solution. The one you can define is an instantaneous reaction rate, how the reaction rate changes with time, by using the tangent of, let's say, the point you're interested on, let's say at 10 weeks, the tangent of the line that touches that particular point. So when you define instantaneous reaction rates, You use the slope of the tangent that touches that particular point in time, and that is the reaction rate in that particular point in time of the reaction. And when people talk about reaction rates, even if they don't qualify them, they tend to talk about instantaneous reaction rates. What happens 50 seconds or 50 minutes or 10 or 15 weeks. So at that particular point in time, that's what the reaction is doing in that moment, without worrying, because it might not be straightforward, without describing what happens before or will happen after that particular point.